In order to understand the universe, it is not enough to build a story. It is much more rewarding to understand a bit more, find out our errors, then fix them. Once you do that, you are way more confident about your story. Hence, today's lecture is about errors. The first error was alluded to in the last lecture. Lenses have chromatic aberration. That's because, think about each side of the lens. It looks like a prism. Prisms break white light into the colors of the rainbow. That causes multiple focal points. Blue focuses closer than red does. What should we do? The technological later answer was a secondary piece of glass with different speeds of light in it, meaning different index of refraction, so to speak. This is a specialized edition. Beforehand, when we used to take black and white images of multiple stars, some of them, the blue ones, were small and very well rounded and focused, while red ones were large and fuzzier. As you can see, that would mean the red ones were out of focus, not that the red ones were larger. Here again is a problem: spherical aberrations. If the lens is not built perfectly, which is a fairly complicated thing to do, then the parallel rays at the ends focus closer than the parallel rays near the center of the lens. This is called spherical aberration. If the lens is not perfectly symmetric, then towards the sides you see stars that, rather than being round, look a little bit like a comet. That's not a comet, but rather something called a coma, which is a result of, again, poor workmanship on the lenses themselves. Another very well-known aberration is astigmatism. Me, personally, I have glasses that correct for astigmatism. Basically, my eyes are kind of puffed up one way, but they are stretched the other way. Therefore, I need an extra glass to orient the light towards my retina so that it really focuses well. Let's look a little closer at how an image is focused by a lens. On the left we have an object, say a faraway galaxy. On the right we have the image, say on the plane of the photograph or the digital device. Every dot coming from the object has to be focused by the lens itself. The middle of the object, or on the optical axis in the middle, would go directly through the parallel plates, and the middle of the object, or the bottom of the arrow, would go to the sides and break down to the real image exactly on the optical axis, and that happens for the dot at the very top as well. This is how a lens should work, but most lenses are built in such a way that the focal plane is not exactly a straight line. Rather, it is part of a huge sphere. That can be corrected with some mathematics, and usually is. But if we just have a regular photograph again, you can see that the top and bottom of the photograph may not be focused while the middle would. The specific distortion described here is easy to understand, so I'm not going to spend many words on it. Instead, let me say the following. We've gone halfway through this first part of the lecture, looking at what happens when a device that you completely relied on should not have been relied on. This is the essence of science. Almost always you get a device that you at first think you could rely on, but usually you shouldn't. The essence of science is to recognize it and know that you're limited. If you think your science is great, if you think your science is perfect, you're a lousy scientist. A much better telescope is a mirror telescope. In order to introduce it, I started by introducing mirrors in general. Mirrors are basically polished metal that take a ray of light and return it, reflect it at the exact same angle. So the way to use the property of the mirror is to curve it in the shape of a parabola. Geometrically, a parabola is a shape that takes all parallel rays and brings them to a single point, hence a focus, same as a lens does. The first telescope that uses a mirror was built by one, you may have heard of him, Isaac Newton. This is his telescope. Technologically speaking, to build a telescope with a mirror, so-called the reflector telescope, you can do one of four things. Either use a Newtonian focus like Newton did, which means take a mirror at 45 degrees angle and basically bend the focus sideways so that it goes to a secondary lens and creates a telescope you can look with your lens at. Have a prime focus like the Hubble Space Telescope, Cassegrain focus, which is our telescope at Baker University, or Coude focus. Now try and use your ingenuity to find the answer to the following question. One disadvantage of refracting telescope compared with the reflector of the same diameter is that try and think what the answer should be. Of course, if the mirror is not perfectly parabolic, it is tough to focus the light into a point. You can't. It has to be parabolic. Industrial design of mirrors is way easier done with spherical mirrors rather than parabolic. The reason is, anything that's spinning creates a circle, and so you can just spin things one way and then the other in order to create a spherical mirror. You then have to use your hands and some sort of a sandpaper in order to make a spherical mirror into a parabola. One can use a correcting lens instead of actually shaping the lens into a parabola. Most telescopes use that patent. Here is one of the most famous reflector telescope dome. Actually two domes. Both of those domes are in Hawaii. Yes. At 4 kilometers or 2.5 miles above sea level, you do get snow even in Hawaii. Here is another famous telescope called the Hubble Space Telescope. It being in space definitely gave it an advantage, but the problem with the mirror was that it wasn't perfectly parabolic. Somebody made a mistake. Let's look at the next picture for a common picture from the Hubble before correction. This is before correction. This is the same exact region of the sky right after correcting that mirror by putting a correction lens in front of it. Here is what we see placed in the focal point of a telescope. No longer do we put a film like we did 100 years ago or even 20 years ago, but rather we put a charge coupled device, which is basically an electronic circuit with some areas that absorb photons very, very sensitively. This is placed in the next picture in the middle. This is a typical camera that you attach to the back of a telescope, and in it there is this chip, electronic chip that you've seen in the previous slide. The sides are made in such a way that the device can be cooled so that every little pixel of the megabytes can be very, very well cooled so that we get no disturbance. This is a typical picture from such camera. In this particular case, in black and white, looking at a place called Lyra and looking at something called the Planetary Nebula, which is a star that exploded and its outer edges are flying apart and only a little bit is left in the middle. This was taken by myself about 10 years ago with a digital camera out in California. This is another picture that I took about 8 years ago on July 4th, 2006, when I have observed an asteroid that passed by Earth on July 4th. You can probably guess which of the light signatures on here is the asteroid. Yes, indeed, it is the line that you see near the center. Here is the same exact asteroid, and the rest of the dots are stars. What I wanted you to note here is the graininess. Remember, in this lecture we're aiming at seeing what's not perfect, not what's perfect. So look at the graininess, look at how square some of those stars look, and how the asteroid doesn't leave a very perfect streak of light. Here is a very common mistake called lack of flats that you get with digital cameras. Again, those are things that can be corrected with computers, but it's interesting to see them so that you can understand what needs correction. In the next few slides, I would like you to see how two stars with the film appear to be much clearer when we're using digital devices at the backs of telescopes. This is the same exact picture, but with digital photography rather than film. This is the same exact picture again, only this time around through 3 separate filters and turning negative. As you can see, the details of those stars are way more clear. Next few slides will be a repetition of the same exact thing.